Earth Day, everyone. Good morning. I'm Chris from Primary Engineer, and I'd like to welcome you to our STATWARS interview session with Professor Richard Betts and Professor Lea Berrang Ford, two incredible scientists from the Met Office. Good morning to both of you. We're here today as part of the STATWARS Climate Change Challenge, our data project which asks pupils to investigate data like the data sets kindly provided by the Met Office, which asks pupils to identify and commit to making 3 changes in their life which will have a positive impact on climate change. Before we get started, the format of the interview session this morning will be that we will hear from both Richard and Lea, who will be sharing some fascinating insights with you about climate change and data. And this will then be followed by a Q&A, as we know you'll have lots of questions to ask them. So I'd like to introduce you all to both Richard and Lea. Richard is a climate scientist from the Met Office and the University of Exeter, and he studies how ecosystems can help slow the buildup of carbon dioxide in our atmosphere, which is caused by the burning of fossil fuels. He works with other scientists and uses data to make predictions and assess future risks, and advises the government on how to address extreme weather caused by climate change. He's currently working with experts from around the world on a large international report on climate change for an organisation called the Intergovernmental Panel on Climate Change, known as the IPCC, which will help the United Nations encourage countries to take action to stop global warming. Lea is an epidemiologist, which is someone who studies diseases. She's also a geographer and an environmental scientist at the University of Leeds. Lea is an expert in the impacts of climate change and is particularly interested in how diseases are carried by insects and how the spread of diseases is affected by our changing climate. Lea works with experts and a range of people around the world to help organisations and especially policymakers understand how to be more climate resilient, which means making them understand how health and the way we live interact with climate and weather. So without further ado, I will hand over to Richard for our first presentation of the morning. Richard, over to you.
Thank you, Chris. So I'm going to give a short presentation on the rise in CO2, carbon dioxide in the atmosphere, and also what we've learned from the global lockdown last year and the reduction in global CO2 emissions that happened, because that was actually quite an interesting learning experience for the scientific community, although obviously it was terrible as a real world event, but nevertheless we learned something about the way the climate system works. This is one of the most iconic graphs in climate science. So it's a graph of carbon dioxide concentration measured at the Mauna Loa Observatory in Hawaii, so in the middle of the Pacific Ocean. And it starts in 1958. The measurements were begun by a scientist called David Keeling, who was aware that carbon dioxide had the potential to drive climate change, and he knew that it needed to be monitored if we wanted to see what was actually happening. And he knew, of course, that, as we all do, that carbon dioxide was probably going to be increasing in the atmosphere because of what we humans are doing in terms of burning fossil fuels and deforesting, which emits CO2 to the atmosphere and causes it to build up. So he started this monitoring in 1958. And you can see that as time goes by, there's 2 things happening in the graph. It goes up to 2 days ago was the most recent measurements. You can see that obviously CO2 is building up in the atmosphere, and that's because we keep putting more and more into the atmosphere, as I said. But you can also see an up and down every year. And that's actually a natural seasonal cycle in the CO2 in the atmosphere, which is caused by the role of vegetation and global ecosystems. What happens is in the growing season in the summer, and this is in the northern hemisphere, as the trees come into leaf and all the grass starts to grow and so on, it draws down CO2 from the atmosphere in the summer months. And then in the autumn, when all the leaves fall off the trees and the vegetation starts to die back and everything, it releases CO2 back to the atmosphere. So it goes up and down every year, but it's going up continuously the whole time. And it's worth noting, actually, that we happen to have passed a rather grim milestone in this just last month. The current concentration of CO2 in the atmosphere is 417 parts per million. So part per million, it means that's for every million molecules of dry air, there would be 400 molecules of carbon dioxide. It's 417 at the moment. Before we started burning fossil fuels in the Industrial Revolution, it was 278 parts per million. So those of you who are good at mental arithmetic will spot that that's a 50% increase. So we have increased the amount of carbon dioxide in the atmosphere by 50% by burning fossil fuels and deforestation. So we've actually changed the composition of the atmosphere quite substantially already in the last 250 years. And that will keep, the CO2 will keep going up if we keep burning fossil fuels. And that's why we're concerned about ongoing climate change, because that's driving the warming of the climate that we're seeing. But one thing we do in the Met Office to help sort of keep an eye on this and help understand how it all works is to actually make predictions of the CO2 concentration rise every year. As I said, it's driven by emissions, but also the uptake of carbon by ecosystems has an impact seasonally. And that uptake actually varies from year to year, depending on the weather and climate. If you get a generally hotter and drier year around the world, that can actually weaken the uptake of carbon by ecosystems. The vegetation doesn't grow so much. So the CO2 builds up in the atmosphere slightly faster when that happens. And then the opposite happens if you happen to have a wetter year around the world. So we try and make a prediction of this, and then we see if our prediction is right to help us improve our understanding of all these feedbacks in the system. But last year, it was a particularly interesting challenge because of the CO2 emissions were reduced because of the global lockdown. This is the forecast that we issued in January 2020. This kind of a zooming in of the last part of the graph that I showed in my previous slide. And on the right-hand side of the graph in red is our prediction we made in January last year of what the CO2 would do at Mauna Loa. We predicted it would increase up to a maximum in May, and then decrease to a minimum in September, and then rise again. And the dotted red line, dashed red line, shows our annual average prediction. So that's what we expected to happen originally. But in about March last year, it became clear that with everyone stopping flying and stopping driving around and global economies almost stopping because of the pandemic, we realized that emissions of CO2 were not as high as we'd expected. So we had to redo our prediction to account for this. However, the prediction when we calculated these was only a slightly smaller increase than without the pandemic effect. Our original forecast had been an increase of 2.7 parts per million, and our revised forecast was an increase of only 2.5 parts per million. So a smaller rise, but still a rise. And that was our updated prediction. And the actual CO2 rise, now we have the measurements coming over the last year. The actual CO2 rise agreed with the revised forecast. It was 2.5 rather than 2.7. So obviously we're pleased we've got that right. But it's quite interesting to see that even though the emissions globally were reduced so much, the CO2 rise was still happening. And the reason for this, you can imagine it a bit like filling your bath with water from the tap. If the tap represents the CO2 emissions, what we're putting into the atmosphere, and the water level in the bath represents the buildup of CO2 in the atmosphere, basically we turn down the tap a bit. So, but the water is still flowing, so the water level in the bath was still rising, just slightly slower. Because CO2 stays in the atmosphere a long time, you see. Once it's up there, it's essentially there for decades or centuries or more. So we just keep adding more in. So the only way we can stop CO2 actually rising in the atmosphere is to stop emitting altogether. Or if we can't stop emitting CO2 altogether, we have to take some out of the atmosphere, either through planting more trees or through new technology. We're just trying to be bit developed, but basically the most of it has to be a reduction in emissions. So the message of this is that we are seeing CO2 rising in the atmosphere. It's building up year on year because of what we're doing to the climate. We have found that reducing emissions can have a small effect, but we need to do much more if we're going to reduce emissions in the longer term. And even just slightly reductions in moving around doesn't make much difference. What we need to do is fundamentally change whole energy systems. We were still burning fossil fuels, for example. So we need to get our energy from other sources that don't include fossil fuels, such as coal and oil. So it underlines the challenge that we have in addressing climate change and stopping the buildup of CO2 in the atmosphere. And that was all I wanted to say. Thank you.
Thank you, Richard. That was truly fascinating, and I know that everyone who has joined us today will have some great questions that they'll be asking shortly about that. I think the bit that I found most fascinating was I hadn't really understood how long the CO2 stays in the atmosphere. So I think there's obviously two things here, because I know that we've got some schools that have joined us today for our other project, If You're an Engineer, What Would You Do?, which is where they're looking to design solutions to problems. So I guess perhaps looking at, as you say, technology that could help, as well as reducing the emissions in the first place, but maybe looking at technology that could tackle the CO2 that's staying in the atmosphere. I don't know, almost like a CO2 vacuum cleaner would be a really nice thing if we could have one, I guess.
Exactly, yes. Yeah.
So, okay, well, thank you, Richard. I think Lea will hand over to you for our second presentation this morning and hear what you have to tell us about data and climate change. So over to you, Lea.
Thanks, Chris. So it was great to hear from Richard, really the scale of the challenge of climate change and decarbonization. And so I'd like to follow up on that by talking about solutions. So what can we do about the climate change challenge? And I think Richard really framed this well, just to show us how significant or how large the changes need to be. So we're not talking about small tinkering around the edges changes to address the climate challenge, but really huge transformations. And so I'm going to jump in and talk about what are the things that we can do about this, or how does the global community look at the challenge of climate change in terms of what responses are available to us. So I'll share my screen. Perfect. Can you give me a thumbs up, Chris, if this is working? Great. So within the climate change community, there are two major ways. There's a few others that we can talk about later, but there are two main ways we think about in responding to climate change. The first is what we call mitigation, and that's basically trying to put less carbon and other gases into the atmosphere, to slow climate change. And that's exactly what Richard was talking about. We need to emit less. And the numbers, or the challenge, is really quite staggering. We need to emit a whole lot less. Even if we went down to zero emissions, net zero today, we would still be facing some heating. And I'll talk about that next. But so mitigation, and to give you some examples of sort of classic mitigation behaviors that we as individuals could use. Some of the major ones that you might have heard of are reducing air travel. Air travel would often have significant significant personal emissions as far as what we as individuals contribute. Having more energy efficient appliances in our households. This also applies to industry. So using less electricity, for example. And the electricity that we do use, having that electricity be greener. So electricity can come from many different sources, and having sources of electricity that are less emitting. So these are some of the classic alternatives which are considered sort of major mitigation strategies. The second approach that we also think about when we're talking about climate change is what's called adaptation. And so adaptation is what we do to prepare for the inevitable effects of climate change. So like I said, even if we went to net zero today, we would still be looking at impacts arising from the emissions we've already emitted in the past. And so there will be impacts of climate change. We're already experiencing impacts from climate change, and these will continue even if we could get emissions to zero. So while trying to reduce emissions, we also have to prepare for the impacts of past emissions. And so that we refer to in the scientific community and in climate policy as adaptation. And so to give you some examples of how our adaptation responses, what they might look like, what's an example of an adaptation response? One might be sort of protection through, say, insurance for flooding, or farmers having insurance for drought to protect people from the impact of droughts, flooding, severe weather events on their property. So that's one example. Another is quite common, especially at municipalities and cities, and this is emergency response. So there might be heat warning systems. If you have respiratory illness, don't go out today because it's very hot or there's high levels of pollution. This also applies to perhaps pandemic preparedness, any kind of emergency response in very hot areas. This might be having cool zones that people can go to, for example. So pandemic preparedness and monitoring is another major adaptation area. And then there's infrastructural responses. So this might be building retaining walls and levees for areas where we expect to flood or where there's sea level rise. If any of you might have seen, if you go to different coastal towns in the UK, you may have noticed actually that you're starting to see stores with flood retaining walls. So actually infrastructural change we're starting to see on the ground, small businesses who don't want their businesses to be flooded. This might involve changing the size of pipes so they can handle larger flood events. This might be walls, dams, anything like that. So there's these two different approaches, mitigation and adaptation, and both are a big challenge. And essentially, we don't have time to do everything all at the same time. We have to be quite strategic with how we make our decisions. And one of my jobs is to help advise governments and to work with, like Richard, I'm one of the authors on the Intergovernmental Panel on Climate Change's its sixth assessment report. And one of our jobs is to help advise governments on how to make these really difficult decisions. And so ideally what you want is for our responses and our decisions and our policies to be put to things that help with both mitigation and adaptation. So there are these options that fall in the middle, which are good for both. And to give you a few examples, using cycling, walking, basically driving cars less, is good for mitigation in that we have lower emissions, but it's also good for other things. So it's also good for adaptation because it improves our health. It's just healthier generally, meaning we're less vulnerable to things like heat, etc. So public transport is a really good, especially the active type, where we're getting healthier, is good for both sides. Another classic one is dietary changes. You'll have heard a lot of talk about shifts in diet. So this is good for mitigation because if we're consuming a diet that has a smaller carbon footprint, that's good for mitigation. But again, it's also good for adaptation because it's in many cases making us healthier and less vulnerable. And then another sort of classic example is what we call nature-based solutions. So reforestation, conservation of forests, and building more green space. So these the biosphere can absorb carbon dioxide in some cases, but also provide cooling. So in cities, for example, there's interest in things like green roofs, there's interest in parks because these can be protection zones from people during heat events. and they can provide a mitigation service. So we refer to these things in the middle as win-win or no regret options, meaning we're pretty sure if we take these approaches, they'll be good for at least one side, hopefully the other, but they're not going to cause unintended consequences. And this is what we need to be doing, both as individuals, but also in the government. We don't have time to hope that what we're doing is going to be best. We have to put strategically our time and money into these win-win options, which are good for both sides. And it's also called no regrets. And the government is asking for this from scientists. So one of the things that I'm often asked to do is tell me which of all these different options out there are the no regrets options. And the reason is that there are other options where there could be regrets. And so these are areas that might be good for one side, but cause unintended negative consequences for another. And a classic example is air conditioning. So you might think, well, during heat events, if it gets hotter and we're worried, well, we can just have more air conditioning and that'll protect us from overheating, especially older, vulnerable people from overheating. And that's true. It's great for health. But the problem is that air conditioning is highly, highly energy intensive. So what's good for adaptation, air conditioning, is bad for mitigation. And there's even been some research that says the number of deaths saved through air conditioning is less than the number of deaths that are created by the health impacts of its contribution to mitigation. So that's one example. On the other side, there are activities that are good for mitigation that we have to be a bit careful about in terms of adaptation. So something like carbon tax, or another example is installing heat pumps, are really good ideas and we need them. But we have to be really careful about how they're implemented. So it's not bad. These are not bad things necessarily, but we have to be careful about how they're done, because something like a carbon tax, we have to make sure that if and when we do this, and when we, for example, mandatory heat pumps might be another example, we have to make sure that we're not creating fuel poverty and inequality so that we're taking some people and making them more vulnerable while we're doing that. So this is not a yes, no, this is not don't have a carbon tax. Some of these things are really good ideas, but this is, we have to be pretty careful that while we're doing a good thing for mitigation, we're not creating other negative other negative side effects for other things. And we call these trade-offs. So it's not very simple. Often the government has to deal with these complex trade-offs and really try and look for the no regrets options. And so what I'd like to do next is zoom in a little bit more into the idea of food and how we judge food. How do we decide personally when we're thinking about our diet, what kind of changes might be good for reducing emissions, but also for other things that matter? Because I think that this is an area where we often hear we all need to be vegan, we all need to be vegetarian. This is sort of a popular thing on social media. And I want to talk about how complicated those decisions actually are and give you a sense of all the different things that we could think about when making our own personal decisions. So I have a little sort of mini quiz for you. You can just do this in your head. What I'm going to do is I'm going to show you two different types of food, and I want you to think in your head about which one might be worse or better. I'm not defining worse or better, okay, but I want you at least to think about carbon footprint, but also other stuff. So, beef versus chocolate. Which is worse? Which has a higher carbon footprint? What about other considerations? Okay. Beef is sort of a classic enemy when it comes to carbon footprint. We often think, okay, there can be no meat. In fact, while beef is typically very high impact, chocolate that comes from a deforested rainforest can actually have a larger footprint than not just any beef, but really low impact beef. Okay. That is harvested locally in sustainability. So high impact chocolate can actually be worse than low impact beef, even though on average beef tends to have higher carbon footprint. What about salmon versus coffee? Well, coffee, and in fact the milk matters too, can actually have a larger footprint than domestic farmed salmon. So what matters here is not necessarily that it's salmon, it's where is your salmon coming from? Is your salmon sustainably farmed? Is your salmon imported from far away, or was it actually, is it actually domestic? And coffee, where does your coffee come from? How is it farmed? So it's often the details matter in this case. And then finally, cheese versus the famous avocado. I'll admit that I actually really love avocados. Where I grew up in Canada, they were local. So I struggle with the fact that avocados are now highly imported. And although dairy is also usually considered particularly high impact for a carbon footprint, avocados that are imported from long distances into the UK can actually have a larger footprint than cheese if it's local, domestically produced cheese. So you can see how some of these comparisons are not as obvious as we might think. And there's all these other questions. It's not just about the carbon footprint and emissions. It's also about, well, which one is healthier? What's good for my diet as well, because that's important for adaptation. And what about human rights? Are there justice and ethical issues with how coffee, for example, and chocolate are farmed? What about sort of the rights of the people involved in this? Is my food sustainably grown? Often that has pretty significant implications for the carbon footprint. And I think what's important is that while you might think, well, my air miles matter, actually, food has air miles too. And food's air miles, how much our food travels. Honestly, our food is much more exotic in many places than we are, and travels all over the world, which has implications in the case of animals for pandemic emergence, a separate issue. But these are things that we might be interested in. And so when we're doing climate policy, we're not just thinking about emissions, but in many cases, we're thinking across all of the sustainable development goals. We're thinking about equity, we're thinking about peace, we're thinking about immigration and migration, and we're thinking about the economy and health and education. And there's often a real story behind every piece of food that we eat. That affects its impact. So it's not just emissions, it's we want to reduce emissions while not creating other problems. So there are two kind of major lessons when it comes to food. So in case you're overwhelmed and think, how could I ever possibly know? The two sort of major lessons in food is that meats and dairy generally do have a larger carbon footprint, but if they're locally produced, it's much lower. So if your meat isn't traveling, then much lower footprint. And related to that, obviously, local products typically have a lower footprint. So those are general rules, but you can see that the picture is much more complicated. So it's not that we just all need to become vegan, it's really that we need to think about the story behind our food. And this makes a sort of a fabulous project to do, is actually to think about the story behind our food. There's a lot of work on carbon food calculators, looking at your dinner plate and thinking about where it came from. And a lot of these are based only on emissions, but one could also imagine looking into the rest of the story behind the food across different sustainable development goals. And actually that's a lot of work that we do for the IPCC and for governments, is not just to look at the data on carbon emissions, but see if there's any data or information on the impact of food more broadly, and to think about how you make decisions when you have these complicated different types of data and different priorities, where you're dealing with trade-offs and you're looking for that gold zone, the no regrets options. And I'll stop there.
Thank you, Lea. That was genuinely fascinating, and I think that whole piece around, you know, the dilemmas, the questions are the really important bit. What we need to be asking ourselves, what we need to be thinking about when we're looking at food and the types of transport we're taking, is to really question things and to be thinking about and looking at the data around those and being able to make informed decisions. But I think it's really interesting, as you say, to make sure that we're not making a decision over here that has this unforeseen consequence over here. So it's really fascinating. I think what I'm going to do now is just go straight into our Q&A session, because I think that we've got lots of people that are waiting to ask questions. If you're wanting to ask Lea or Richard a question, please use the Q&A function at the bottom of your screen. There's a little speech bubble thing that says Q&A, and you can type in your questions there. It can either be a general question, or it can be, you can also say, if you wanted to ask either Lea or Richard in particular, you can state who you want to address your question to. So if those questions are starting to come in now, and I can start sharing those with Lea and Richard and asking them. So we've had one question immediately that said, what is the difference between global warming and climate change? So would either of you like to tackle that one?
Yeah, I'm happy to answer that. So global warming is a part of climate change, really. Global warming is the increase in the average temperature of the world. Well, my colleagues in the Met Office and other institutions around the world gather weather data hour by hour, day by day, and then put this together to not only to monitor the weather, but also to see how much the average temperature of the world is changing. And the world has warmed by over 1 degree Celsius in the last 100 years. So that's global warming. And we know it's being caused by the increase in CO2 in the atmosphere that I talked about. Climate change is perhaps more general because it's not only temperature that's changing, but also we're changing patterns of rainfall. Some areas are getting wetter, some areas are getting drier. So in many cases, rainfall is falling heavier when it does fall. So that's a wider kind of picture of climate change, but that's driven by global warming in the longer term. But also it does change year to year naturally anyway. But overall, we're driving this longer term change. So that's the difference between the two.
Brilliant, thank you. And following straight on from that, South Hetton Primary 6 have asked, what method is used to measure CO2 in the atmosphere?
Yeah, a great question. Yeah, so the basically there's a Ralph Keeling's. I mentioned David Keeling, who invented that CO2 graph where he started the measurements. His son Ralph now keeps up the measurements at Morning Lair Observatory. Their team use a gadget which uses lasers basically, and the amount of light absorbed by the laser is affected by how much CO2 there is. So that can give you a really precise measurement of the amount of CO2 in the atmosphere.
Brilliant, thank you. We've had a couple of questions. So we've got one from a school who are asking, what qualifications would you need to work for the Met Office? And linked to that, we've had another question saying, what are the new and developing careers in the Met Office that maybe people that have joined us today could aspire to in the future?
So I guess that one's for me as well. Then, if I'm the Met Office employee here, so if you want to be a scientist in the Met Office, most of us have degrees in things like maths and physics, but not everyone. Some have degrees in other aspects of science, like biology or ecology or geography and so on. But most people, because we do the kind of computer modeling and all the calculations, most of us are mathematicians or physicists. Elsewhere in the Met Office, there's a huge organization. So we have not only scientists, but also the weather forecasters as well, who may have a degree in geography or so on. And like any organization, we've got IT experts. So any qualifications in IT are really helpful. We have huge supercomputers as well as desktop computers that do these calculations. So we have a very big and valuable IT department that keep everything running. And then you got all the other usual stuff like the people that work with advising governments and so on. So they might be communications experts, the HR department who have skills about looking after people, the finance team and so on. So generally, if you want to be a specialist, science is the thing. But if you want to work elsewhere in the office, pretty much anything, basically.
Yeah, thank you. And I think that one of the things that I took from that as well is that, you know, all of the data, you know, and this is what people that are doing the STATWARS project are understanding, is that it's finding out about data and interpreting and interrogating data, but it's also, as you said, really important to be able to communicate about data. And that's something that the young people on the project are doing. Moving on to the next question, and I'm running through very quickly because we've got lots coming through. This one's for you, Lea, and it's a question around batteries. Are batteries bad for the environment, and how could batteries be revamped or improved to be better? And I guess that links in with the trade-off piece that you were talking about.
Yeah, so good question. I think you can think about this with the reduce, reuse, and recycle. It would be better if we simply had used less. Okay, so in a sense, first thing we do is have less need for power. Batteries, it depends on what you're comparing batteries to. So batteries are typically, if you're talking about the small sort of AA ones, the damage is typically in sort of chemical waste. And so it depends what type of chemicals are used. There are also sort of large industrial battery approaches. There are certainly efforts being made to come up with different technologies out there. So there's no easy answer to that. I would argue that the first thing we would like to do is probably minimize our energy use, and then in all cases where possible, have the energy use that we are using be from green sources. And batteries, yeah, the waste is chemical. It's the emissions would be involved in the manufacturing of the battery, less so than in the actual use of the battery.
Okay, and would things like, if you could recharge batteries from solar panels, for example, if you had small solar panels to recharge your little batteries that you're using at home, presumably that would be better because there's less waste, you're using less batteries and you're using green energy to charge it. Does that, you talk about sort of mitigation, does that make it slightly better?
Yeah, so it's the context around the battery. So in many cases, if you use, you'll have seen houses often have photovoltaics or sort of solar panels that can either be used to heat water for the house or to a different type to generate electricity. And often that electricity is stored in a battery. So it's sort of where the energy for the battery comes from. In that case, you're converting light energy. Some of you may be studying different forms of energy at school. I know it's on the year 7 curriculum. Maybe converting energy from light into chemical energy in the battery, and then that's moved into electrical energy. So the more in that sort of energy flow process you're removing non-renewable sources, the better.
Good, thank you. We've got a question for both of you because you both work with a huge number of different experts and organizations around the world. We've got questions around what that's like to work with different experts around the world in this field. What kind of skills do you need to do this? And I guess in particular to work with governments. And then if we do that one first, and then I've got another one for you, Lea. So if you could both talk a little bit about, working collaboratively around the world, that would be great.
Sure. Why don't I start, Richard, and then you can take over. It's really fun to work with other people. When we used to go to in person pre-COVID, our IPCC climate meetings, it's a little bit like summer camp for climate scientists. We get to hang out with some of the most interesting people in the world working in our field. And answering real problems and trying to come up with real policy solutions. It's one of my favorite parts of my work. When I work with remote indigenous populations in Amazonian Peru, Uganda, and the Canadian Arctic, and I get to meet people from entirely different cultures. So it really sort of broadens my personal horizons And so it's by far one of the best parts of my job. And you also realize, you also get a sense of what your skills are and how they contribute to the whole, and how you can bring together different people's skills. So quantitative skills are quite useful in this field. I'd like to add to Richard's comment about quantitative options. I'd like to add to that 2 areas of quantitative analysis or highly quantitative work that are also quite useful. One would be econometrics. I think econometrics for climate change is going to be a huge emerging area. We just can never find enough people on econometrics for adaptation in particular. And what I did was epidemiology. So this was basically modeling, similar to what Richard was talking about, but modeling diseases. And of course, that's really important, and even more important under COVID, and quite relevant to climate change. So those are highly quantitative fields that aren't necessarily specifically in maths, meteorology, or physics, but are still really using data. And the one thing I would like to add is that I think there's increasing value placed on people that not only know or have some quantitative expertise in whatever field you're passionate about, but also have some broader expertise. So I personally love geography because it exposes people to sort of a wide range of interdisciplinary knowledge, so that even if your expertise is quantitative, that you know a little bit about these qualitative methods, because sometimes you can't answer your question just with quantitative data set, and you have to sort of reach out and bring in different methods and different skills to get the full picture. And the co-benefits example I gave is a perfect example of where there's just not quantitative data on everything. So we sort of have to synthesize different types of evidence to actually get a good answer to the questions governments are posing us. So quantitative skills are good, but also being able to speak to other people, to understand other methods, to have a bit of interdisciplinary around your central skills.
Brilliant. Thank you, Richard. Did you want to add anything to that?
Yeah, so similar really, that I think the working with experts in other parts of the world and other disciplines of science and other academic fields altogether is really important, and I really love that as well. No one possibly knows everything. We all rely on each other, and especially with a global issue such as climate change, it's really important to have the knowledge and the understanding of local experts about what's happening with the climate in their area. One of the things that's important is to be able to listen to each other carefully and really try and understand what each other are saying, because different scientific fields have different technical language and so on. It's actually quite a challenge to get physicists, economists, epidemiologists, social scientists all working together, because often to start with, we don't understand what we're talking about because we use our own jargon. So we have to listen to each other and challenge each other and question each other to make sure we understand each other properly. And that challenging each other is also a really important part. You don't just believe everyone. If someone is saying something and you don't understand why, it's perfectly legitimate to ask them to back it up with evidence, and asking for evidence and clarification is really important. And that's an important part of science, is testing each other. And the IPCC report that Lea and I are both working on, the reason that's important and authoritative is because so many people are involved, and we challenge each other, and we are challenged by reviewers as well to defend what we're saying. And the outcome, it's hard work, but the outcome is it's an authoritative body of work because everyone has agreed to it and said, yes, this is right.
Yeah, I think you're right. And I think it's really important to be questioning all of the time. If somebody presents something to you, you don't just accept it. You need to see, the evidence and the data to back it up, which is really important. There's one specifically for you, Lea, and then one for both of you. So Lea, we've got a year 3 class who would like to know, how do we know if the food we eat has a big footprint or a big carbon footprint? And then for both of you, we've got another question, which is, what is the greatest threat posed by climate change?
So I'll start with the easier one, the food footprint question. The second, we could spend all day on that. So food footprint, it can get really complicated really fast, but to keep it simple, knowing where your food comes from is a good place to start. So I recently went into my butcher with my year 4 son, and we asked, where does that chicken come from? You know, did that chicken come from a mile away, or did that chicken come from far? And what about the bacon? Where does that come from? And we find out about our food, where it comes from. You know, is this a lamb that was made in New Zealand, frozen, and flew all the way from New Zealand to the UK, which actually a lot of our lamb does? Or is this one of those little lambs I saw on the fields, looking at least relatively happy, and just comes from a few miles away? The same thing applies to fruit and vegetables. If you pick up fruit and vegetables, they often have a sticker on them, which tells you where they're from. And so if the food you're eating has traveled really, really far, then it has more miles. So the easiest thing is to sort of inform yourself of sort of nationality of the food and where your food is coming from and how far it travels. And then the other generalization is that meats, particularly red meats and dairy, tend to be higher. And you can Google a lot of this stuff and get some nice graphs that give you a little bit of a sense of where things are coming from. So that's kind of the fastest and quickest tricks on how to judge where your food is coming from. And I'm going to let Richard take the first stab at the much trickier second question.
Yeah, so the greatest threat posed by climate change. Well, first of all, I want to say that it is still possible to avoid the worst. We are not yet committed to climate doom. I want you to be reassured about that. We can avoid the worst, but we have to do something about it. What exactly is the greatest threat? Probably a matter of opinion. I would say, personally, overheating, heat stress in tropical countries which have high populations. So, for example, in the Indian subcontinent, you've got India, Bangladesh, Pakistan, millions, I think probably over 1 billion people live in that area alone. Very, very highly populated countries. They're very hot already. They're also very humid, and humidity. So when it's kind of a wet heat, it feels very sticky. That's particularly dangerous because you can't cool yourself by sweating. And there's been some really dreadful heat waves in Delhi in recent years, for example, in India, there's been lots of deaths. That's an area where heat stress and in heat waves will be the worst and hit the most number of people. So that's one thing that really concerns me. But as I say, there's probably different views on what the greatest one would be. Lea might have a different view.
I totally agree with Richard. If I had to choose, I'm going to choose two, just because I can't decide. One would be, to add to Richard's, is extreme weather events in general. So storms, floods, drought, and the implications that has on people's food sources. So just ability to grow enough food given these extreme events. And the second I wanted to throw in, because I think we don't often think of it, is the threat to global security. So often the implications of climate change aren't just the event itself, but what it means when people can no longer grow enough food and have to migrate, or what it means when our water resources are getting depleted and you start to get conflict around the remaining water resources. So there's often some pretty important spin-off effects, like conflict, like major migration. We've got entire islands in the Pacific that are anticipated to disappear under climate change. And those people and those governments are actively planning, where are we going to move? You know, what country are we going to negotiate with to buy land or integrate with? So international migration and threats to security, I think are quite important implications. And that can even happen before an impact, as people anticipate what the impact will be, and as resources start to get affected. So there'll be all of those spin-off things that we have to remember and keep an eye on. And in fact, during major events, and actually COVID is similar to this, but during major events, it's often not the number of people who sort of die or are harmed during that event, but often there's more harm or more problem from all of the subtle implications to people's jobs, people's livelihoods, people's mental health. So I think those impacts are harder to quantify and sometimes more important.
Yeah, and as you say, not necessarily things that we immediately think about, but we should be thinking about. Thank you, both of you. Moving on to the next question. Somebody's asked about the future of power production. So they're saying that there are boilers and even entire towns now being run and tested on hydrogen. What do you think the future of power production looks like? And do you think hydrogen will continue to be involved? Who would like to take that one?
Do you want to take that one?
Yeah, I can take that one. I think we're going to need lots of different ways of producing power, so long as none of them involve fossil fuels. So basically, that's the bottom line. That but there's other ways of getting power from renewables. So wind farms, solar panels, nuclear power is low carbon. But hydrogen as well is a way of producing energy, and there's a lot of work going on in that area now. So I think that all of these things will be used. I don't think there's one single solution. That there's pros and cons to all of them. So yeah, all of the above.
Yeah, a kind of mixture of, and I think also as well, previously we've kind of relied on the national grid and energy coming from one big source, but I think there seems to be much more of a localized approach now, and that seems to be gaining momentum. Do you think that will really help if maybe smaller areas, maybe like a town takes responsibility for its energy consumption and looks at having ways of generating electricity as a town for the houses in that town? Does that seem to be a good model to use?
I think it depends where you are, really, because with this kind of thing, it's like what Lea was saying with food. A lot of these things are actually incredibly complicated when you get down to the sort of the individual details. So something that works in one place may not work in a different place. So you just have to have a look at it in a case by case basis, not only within the UK but also around the world as well.
Yeah, thank you. We've got roughly about 10 minutes left, so moving swiftly on, we've got a question around Richard, you mentioned heating due to climate change, and the question is, has climate change got anything to do with the crazy freezing weather that we recently saw in Texas?
Ah, right. So that's exactly the kind of thing that we do a lot of research on, because it's a very difficult question. Probably no is probably the current answer, I would say. You do tend to get, overall the world's getting warmer, obviously, and we expect hotter extremes more and more. Generally speaking, we'd expect fewer cold extremes, so on the whole less cold weather. However, if the climate change, and this is the difference between climate change and global warming, if it does shift wind patterns, then it can make more unusual colder conditions in some cases. And also with snow, it rather strangely you could get more snow in places that are already cold, because, as I said, if we're changing the amount of water in the atmosphere and changing rainfall, that will fall as snow in cold places. So if you've got more water that's falling out of the atmosphere as snow, that can rather bizarrely be a consequence of climate change in a place that's already cold.
So we had that in Montreal on the really cold days, it wouldn't snow.
Right.
It gets too cold, it doesn't snow. It snows at this sort of -0 to -15, and then when it gets too cold, it won't.
Yes. Yeah. Exactly. Yeah. So, so this is why it's such an interesting and important area of science, because a lot of these questions are very difficult to answer. But as I say, I think the current understanding for Texas in particular is probably no, it probably wasn't a climate change effect. Weather just does happen still, and it always will do.
The unpredictability of it. St. Luke's Primary School have asked, when did climate change start? And do you know when it could end if we follow more eco-friendly behaviours?
So should I take that one, Leah?
Sure.
The world's climate has always changed naturally over the whole millions and billions of years of the Earth's life. Human-caused climate change, which is added on to the natural climate change, which is what we're seeing now, we started to see that just over 100 years ago. As I said earlier, the Industrial Revolution was when we started to burn fossil fuels and build up the CO2 in the atmosphere more. The effect of that started to become obvious about 100 years ago and become really clear in the last 50 years. So that's when human-caused climate change happened. The second part of the question was when it would stop, did you say, Chris?
Yeah, you have an idea when it could potentially end if we start making changes and follow more eco-friendly behaviours?
So because the CO2 stays in the atmosphere a long time, as I said earlier, the changes that we've already made happen will be with us now for all our lives. And that's why it's important to take action soon, because if we keep adding more climate change, that will be with us for the rest of our lives as well. So it's not when it's going to, we can't take it away, but we can stop it getting worse. There's an international agreement called the Paris Agreement. All the world's governments have signed up to. They've agreed to try and limit global warming to well below 2 degrees Celsius. As I said earlier, we're at 1 degree Celsius warming already. The aim is to limit to well below 2, and ideally only 1.5 degrees Celsius warming, although that might not be possible anymore. If the world gets its act together and really reduces emissions, then that could be achieved sometime in the middle of this century. So we've probably got another at least 20 or 30 years of further change to happen, at least. So we are going to see further change. And this is why the adaptation that Lea was talking about earlier is important, because some things are already happening and we've just got to live with them.
And we've got to continue to, as you say, over the next 20 years, make not contributing and making it worse.
But we can still avoid the worst in the long term. Yeah.
Brilliant. Lea, I know we're kind of running out of time, and I'd like you both to sort of share some parting advice. But before we do, I'd really like to hear from you, Lea, a bit about diseases and climate change. So how is climate change affecting the spread of diseases? Germs or bacteria, for example, or, I think particularly we mentioned at the beginning about insects. Does climate change affect insects that would perhaps be spreading or spreading diseases?
Yeah, this question has become even bigger now that everybody's learning a lot more about diseases under COVID. And so there is a really strong link between climate change and diseases. Just to give you two of many examples, the mosquitoes that carry malaria or other insects that carry things like Lyme disease, West Nile fever, those mosquitoes, their ability to replicate and survive depends on the weather. And even more importantly, the little mosquito pathogen itself, its ability to replicate depends on the weather. So it has to be, and this is why malaria is mostly in warmer areas, because it needs it to be hot enough in order for it to finish its life cycle. So if we get changes in weather, temperature, but also precipitation matters, you can get spread of the areas where things like malaria are capable of transmitting, or you can get sort of a longer malarial season. So climate change is one of many factors that can spread diseases. Now, the UK has had, and Canada have had malaria in the past. So while climate is only one of many factors, there's also a lot of reasons for why we don't have malaria now. So it's not suddenly like it's going to explode in areas, because we've got good healthcare systems and that sort of thing. So that's kind of one of the main ideas. The other one is that when you have heavy rainfall events, so more, not necessarily even flooding, but just heavy rainfall, that can flush all this sort of agricultural excrement, poo, basically, into our water system. And sometimes that can overwhelm our water treatment, and you can get waterborne disease outbreaks. So even when you have a water treatment plant that normally works well. So we have to make sure our water treatment plants are up to snuff with new weather. But it's not just that. Actually, the causes of climate change, including things like deforestation, are actually shared with pandemic risk. So something like COVID was not caused by climate change, but the things that we're doing, deforesting, for example, actually contribute to climate change and contribute to COVID risk, because most emerging infectious diseases jump the species barrier from animals to humans. Our infectious diseases come from animals at some point. So if we're incurring into forests and sort of discovering new wild animals and having more contact with wild animals, the chances of us having an emerging disease are higher. And the more we eat different animal meats, the more we have these huge populations of chickens and pigs moving around the world, getting lots of air miles and meeting each other. And what we get is you get this not only animal mixing, but pathogen mixing. And that's where H1N1, a recent flu, came out of that, animals mixing together. So dietary habits, like lots of meat eating, also contribute to climate change and contribute to COVID risk. So there's different places where our relationship with disease and our relationship with climate intersect.
That sounds absolutely fascinating, and I wish we had more time to talk about that. We need to wrap up now, sadly, and we've had some fabulous questions, but I think it would be great if you could both perhaps leave a parting thought or parting climate advice for our young scientists that have joined us today. That could be something specific to your area of expertise, or it could be something more general, but perhaps if you could give some parting advice, that would be wonderful before we finish for the morning. Lea, would you like to go first?
Sure. Some of this can cause a bit of doom and gloom and worry, but I think every generation has its major challenges, from world wars to COVID, which I think is actually going to make you, the younger generations, more resilient. And one of the challenges that your generation, even more so than ours, has will be climate change. And so this will be one of the things that's part of life that you deal with. And it doesn't need to be scary. If anything, it's an opportunity. It's an opportunity to say, hey, you know, I can have influence, and I can tell my parents, I'm going to make better decisions than you did. And it's an opportunity for new types of jobs. So life is full of sort of difficult challenges, just as human beings. I think COVID has been useful in teaching us resilience and showing us how much communities and countries and people can change in response to a challenge. And it's a reminder that we can make major shifts in our lifestyles. And those are things we're going to need to do for climate. And your generation will be important leaders. So I think there's a lot of optimism here.
Brilliant, thank you, and great opportunity. Richard, your parting thoughts, please.
Yes, thank you. So, well, there's a final question in the Q&A asking what gives us hope, and I think that's a great one to finish on. The two things that give me hope are that humans are clever and resourceful, and we can solve problems. And we've talked a lot about the science and so on, and communicating the science. And I think all these things together, we are understanding the problem, and people are now recognizing that we need to do something and what we need to do. So that is giving me hope, but also the passion and enthusiasm of young people is also giving me hope as well. It's great that everyone's here today to learn about this, and I see a lot of young people, being very active, making their voices heard now. So that gives me a lot of hope as well. So I guess if what I would love would be for the audience here to really continue along those lines, get into either science or other areas of learning where you can really find out what's happening and use it and talk about it as well, and use it to make a difference in the world, because the future belongs to you guys. So please help us to sort it out.
I think that's a brilliant place for us to finish for this morning. Thank you both, Richard and Lea, for your time, for your insights and your thoughts, and for answering the questions. Thank you to everyone that joined and for all of your brilliant questions. It just remains to say that I think there's a lot here for you to take back and apply to the STATWARS Climate Change Challenge, and also to the If You're an Engineer, What Would You Do competition. And thank you again, Lea and Richard. And it's been a pleasure to meet you both and to hear all of your insights into climate change. Thank you very much.
Well, thank you for having us. It's been great. Thank you. Cheers. Great questions.